Um, in this video, we are going to discuss about a case study regarding implementation of smart fabric system for monitoring ECG. ECG means electrocardiogram and respiration. So, what is mean by electrocardiogram? Depolarization of the heart is the initiating event for cardiac contraction. The electric current that spread through the heart are produced by three components: cardiac pacemaker cells, specialized conduction tissues, and heart muscle itself. The ECG, however, records only polarization, that is stimulation, and depolarization recovery potentials generated by the working atrial and ventricle myocardium. The ECG records the complex spatial and temporal summation of electrical potential from multiple myocardial fibers conducted to the surface of the body. This principle accounts for inherent limitation in both ECG sensitivity activity from certain cardiac region may be cancelled out or may be too weak to be recorded, and specificity. The same vectoral sum can result from either a selective gain or a loss of force in opposite direction. ECG signals are detected by means of metal electrodes attached to the extremities and chest wall, and then are amplified and recorded by the electrocardiograph. So usually we are going to use totally 12 metal electrodes, which is placed on the chest of a human body. You have a unipolar leads and bipolar leads and chest leads. Totally you have 12 leads, 6 for chest and 6 for unipolar and bipolar. The ECG leads actually display the instantaneous difference in potential between the electrodes. The clinical utility of ECG derives from its immediate availability as a non-invasive, inexpensive, highly versatile test. Bipolar and unipolar lead configuration. ECG lead in a graphical description of the heart electrical activity occurred with different electrodes that are reading the same event but from different angles. Every lead represents a difference of electrical potential measured at 2 points of the body. The ECG signals can be acquired with the help of a couple of electrodes, one positive exploring and one reference negative. The reference electrode can be composed of a combination of 2 or 3 electrodes. ECG leads may be subdivided into two general types. One is unipolar lead and another one is bipolar lead. A bipolar lead consists of two electrodes placed at two different sites. These leads register the difference in potential between these two sites. The actual potential at either electrode is not known, and only the difference between them is recorded. One electrode is designated as positive input. The positive potential at the other negative electrode is subtracted from the potential at the positive electrode to yield the bipolar potential. Unipolar leads, in contrast, measure the absolute electrical potential at one site. This requires a reference site, that is, a site at which the potential is considered zero. The reference site may be located far away from the active electrode, or as in clinical electrocardiography, the reference site is a specially designed electrode configuration. The unipolar recording is then potentially sensed by a single electrode at one site. The recording or active or exploring electrode in relation to the designated zero or clinical electrocardiographic lead system. The standard clinical ECG includes recordings from 12 leads. These 12 leads include 3 bipolar limb leads, lead 1, 2 and 3, 6 unipolar chest leads, V1 through V6, and 3 modified unipolar limbs lead, augmented limb lead, AVR, AVL and AVF. RL means right left, F means foot. The limb lead record potential transmitted onto the frontal plane, and the chest lead record potential transmitted onto the horizontal plane. So it shows the lead 1, lead 2 and lead 3 structures. Okay, usually the right leg is considered as a reference. So one is AVR, AVL and another one is AVF. Okay, next one is bipolar limb leads. Bipolar limb leads record the potential difference between two limbs. As bipolar leads, the output is the potential difference between the limbs serving as positive and negative inputs. Lead 1 represents the potential difference between the left arm and right arm. Lead 2 display the potential difference between the left leg and the right arm, as shown in the figure, right? And lead 3 represent the potential difference between the left leg and left arm. The electrode on the right leg that is not included in this leads serves as ground connection. Unipolar precordial leads and Wilson central terminal. The amplitude of the electrical signal recorded from the standard limb leads can be small when compared to the electrical activity of the nearby skeletal muscle. In addition, the standard limb leads provide only 3 views of the heart. The augmented unipolar leads were conceived as a way of increasing the dimensity of the signal and providing a different view of the heart activity. The augmented unipolar leads use the same electrodes as the one used for the standard limb leads. The only that changes is how these electrodes are connected. For each of the augmented unipolar limb leads, represented by the prefix AV, two or three electrodes are connected together and brought to ground. The remaining electrodes become the exploring or active lead. In case of any unipolar lead, current flowing towards the active electrode produces a positive deflection, while current going away from the electrode producing a negative deflection. One of the limitations of either the augmented unipolar leads or the standard limb leads is that they look at the heart from the same plane. In order to view the heart from another plane, the 6 chest leads have been introduced. Each of these leads is a unipolar lead. By using these 6 leads, it is possible to get information about the anterior and the posterior parts of the heart. So this is your Wilson terminal W, okay, which is placed on the chest lead. Next, the positioning of the electrodes. The implementation of a standard distribution of the electrode in a wearing monitoring system is limited by the available space on the body and by the capability of maintaining good contact between the electrode and the skin during prolonged use of the system. For these reasons, a reduced number of leads is usually implemented, as in the configuration depicted on the left side, where the two unipolar precordial V2, V5 leads within the Wilson central terminal and the three etho1 bipolar limb leads have been selected. These are the positioning of the electrodes. You can see V2 and V5 at the left side of the picture, and the right side of the picture you have SEAIG, right? So what does E means? It's at the level of the fifth on the lower sternum. Okay, so these are the position ASIG. Okay, if you look at the picture, you can able to see the description, right? Next one is respiratory signals. The respiratory systems consist of the lungs, the conductive airways, pulmonary vasculature, respiratory muscles, and surrounding tissues and structures. Two parameters are particularly important in monitoring the lung function. One is breath rate, that is breathing rate, BR, expressed as the number of breath per minute, is a parameter characterized by high sensitivity. Also, if the variation detected are not specific to the respiratory dysfunction. The inspiratory fraction is the ratio of inspiratory time to the total respiratory time. Low value of this ratio associated with an increase in the expiratory phase may be an indication of an airway obstruction. Example, asthma. Low values are also detected while a subject is talking, and high values can be measured during sleep, especially if the subject has difficulty in breathing. Continuously, the kinematics of the chest wall that are associated with changes in thoracic volume. Although the respiratory system is very complex and its analysis requires the identification of multitudes of parameters. Several methods and strategies have been used to measure. In particular, three measurement strategies are compatible with wearable application. The first is based on the use of piezoresistive sensors for monitoring movements correlated to respiratory activity. The second is based on the use of inductance plasmography. A conductor is integrated in an elastic band to form an inductor. The third method is based on the impedance plasmography. Body impedance is conventionally measured by collecting the potential drop caused by the movement of charge due to the injection of a high frequency and low intensity current through two electrodes. The application of smart fabrics in healthcare has gained significant attention in recent years. So now we are going to see about some introduction regarding the case study. Okay, so this case study explores the development and implementation of a smart fabric based system for monitoring ECG and respiration signals. ECG means electrocardiogram. The integration of wearable technology with textiles allows for continuous and non-invasive monitoring, providing valuable data for healthcare professionals. So what is the methodology we are using here? First one is a fabric development. A conductive fabric is selected as a base material for embedding sensors. The fabric is engineered to be flexible, breathable, and skin friendly to ensure comfort during prolonged usage. Second one, sensor integration. ECG and respiration sensors are integrated into the fabric using conductive threads or inks. These sensors detect and capture the physiological signal of the wearer. Third one, signal processing. The captured signals are processed and filtered using signal processing algorithm to remove noise and artifacts, ensuring accurate data. Fourth one, wireless communication. The processed signals are wirelessly transmitted to a receiver or a smartphone application using Bluetooth or other suitable wireless protocol. Last one, data analysis and visualization. The received data is analyzed and visualized to provide real-time insight to healthcare professional or the wearer. So what are the applications and benefits? The first one is continuous monitoring. The smart fabric systems enables continuous monitoring of ECG and respiration, providing valuable data for early detection of cardiovascular or respiratory condition. Second one, remote patient monitoring. Healthcare professional can remotely monitor patients' vital signs, reducing the need for frequent hospital visits and facilitating timely intervention. Third one, home healthcare. Smart fabric empower individuals to monitor their own health from the comfort of their home, enhancing patient engagement and promoting self-care. Fourth one, sport and fitness. Athletics can utilize the smart fabric systems for performance monitoring and optimization, tracking their physiological response during training or competitions. Results. First one is accuracy. The smart fabric systems demonstrate high accuracy in capturing ECG and respiration signals, comfortable to traditional medical grade devices. Next one, comfort. User report a high level of comfort while wearing the smart fabrics due to its flexibility and breathability. Next one, usability. The system is user friendly, allowing individuals to wear fabric comfortably without hindering their daily activities. Real time monitoring. The wireless communication enables real time monitoring, allowing immediate detection and response to abnormal cardiac or respiratory events. Conclusion. The case study demonstrates the successful development and implementation of a smart fabric system for monitoring ECG and respiration. The integration of wearable technology with textiles offer promising opportunities in healthcare, enabling continuous, non-invasive and remote monitoring. Smart fabric based monitoring has the potential to revolutionize healthcare by improving patient outcomes, reducing healthcare costs, and enhancing overall well being. Further, research and developments are necessary to refine the technology and expand its application. Some of my reference for making these videos I have given below. First one, Annalisa Bonfiglo and Dilo D. Rossi. Wearable monitoring systems, Springer 2011. Second one book is Gong Zong Yang Body Sensor Network, Springer 2006. Third one is Fundamentals of Internet of Things, IoT and Wearable Technology Design, IEEE Press, Willy Higher Road. Fourth one, Wearable Sensor Fundamentals, Implementations and Applications, edited by Edward Sassunovo, second edition.